Well, anyway, welcome everyone. First of all, exciting news. We should be excited in 2020. Looks like we've got a vaccine, so that's really exciting. So maybe we will all see each other one day soon on campus. Seems like things will be getting slightly back normal in the spring. So we are making progress. Okay, so as far as the exam goes, the multiple choice scores looked pretty good. Maybe I can publish those if you're curious about how you did on that part. So that grading is done. I can publish that after class if you want to check out how you did. And I'll get cracking on grading the rest of the exam over the weekend as well. I don't think I'll finish it over the weekend, but I'll do the best I can. Yeah, and so then what I want to do today is just pick up with functions. So we started this a little bit earlier in the semester, and so we'll pick up with these ideas. Maybe we'll get a little bit into sequences in the next chapter as well. And I would say that these are pretty good launching points into Math 4310, real analysis. Is going to be looking at proof techniques applied to functions. So that's makes sense to kind of take a look at some of these ideas that you'll delve into a lot deeper in if you're going on to take that class. But any questions before we get started for today? Okay, so on the reading quiz, hopefully you just kind of refreshed your memory about what the definitions for function, domain, codomain, range are, and we also talked about what it means for a function to be injective. We did not get into surjectivity, so that makes sense to pick up from there. So both of these ideas, injectivity, surjectivity, are in 12.2. So just to kind of refresh ourselves. So we were dealing with relations, which didn't have to be functions. So now we're going to take a look at a very special relation where each element in A gets paired with only one element in B. So that's our function rule. The domain are the inputs. The codomain are the set where the outputs live. And the range would be all of the outputs that are mapped to by this function. And so a function one-to-one if distinct elements get mapped to distinct output values. So any questions about those concepts? Okay, so then what a surjective function means is, more colloquially, we would say that the function is onto. So those terms are used interchangeably. And what this means is, in general, right, the codomain and the range are not necessarily the same. So when a function is onto, that means every element in the codomain is mapped to from some element in the domain. And sometimes the best way to get comfortable with these definitions is to just take a look at examples of what's something that is surjective, what's something that's not surjective. So basically, we some kind of terminology is we call things in the domain are sometimes called called the pre-image, and things where they get mapped to in the range would be called the image. So we might use some of this language as well. So basically, if something is onto, what it's saying is the codomain is the image of something in the domain. So the proof technique here is what we'd like to show is for every element in the codomain B, that there exists some element in A that is mapped to that element in B. So in this case, that would be called the pre-image. Or we can call y the image of x. So that's how we could use that terminology. And then if a function satisfies both an onto and a one-to-one property, so if it's both injective and surjective, then we call that map bijective. And these are really nice maps in general. They have some really nice properties that are, that are going to be functions that are bijective are particularly interesting to take a look at. Okay, so let's take a look at some examples. So let's say here we are looking at the function f, which is mapping from integers to the integers, where f of a is defined as the absolute value of a. So just to check these things, so the question is this injective, surjective, bijective? So certainly it's a function because for each value, we plug it into the absolute value, we get only one output, so that's fine. So let's see. I was wrong. Dog's gone. Oh well. So for this to be injective, right, that means it should be one-to-one. So that means each output should only have one input that was a pre-image.
Not injective.
Why not?
Because 1 and -1 both result in 1.
Right, so that's basically contradiction there, right? If it's injective, we can't have two different inputs that give me the same output. But let me just say, like, just because you're not injective doesn't imply that you're not surjective. So these are different properties. So it's not one-to-one, which right away tells us that it's not going to be bijective. So for surjective, here we're checking onto. Okay, so so far, right, we know that the domain are the set of all integers. The codomain is the set of all integers. And the question is, right, is the codomain equal to the range? Does everything in the codomain have a pre-image? And then if so, it would be onto. So what's the range of this function?
The range is only positive integers.
Yeah, that's right. So the range also includes 0 and the positive integers, right? So it'd be like non-negative things. So the range here is not equal to the codomain. So that rules out the fact that it would be surjective. But if we kind of want to show that, we can just pick a value like the number -1, which is in the codomain Z. There's no integer which would map to -1. So -1 has no pre-image, not onto. Any questions about that? Okay, and just a couple of announcements while I'm thinking of it. So usually you have homeworks due on Monday. There's not going to be homework on what we talked about today. So they'll be, so is next week is the last week before Thanksgiving break, right? And then we have 1 week after that. So you'll have one more homework assignment that will be due the Monday after Thanksgiving break. That'll be the last one. Sorry. I know you're sad about that. Okay, so we're almost there. So I will get that up so you can start working on it if you like, but it's not going to be due next week. Okay, so now let's think about this function h, which is mapping from the real numbers into the real numbers, where we're going to define h of x as x squared. So let's injective, what do you guys think? You can give me yay or an A. Okay. Not injective, right? So why is that not injective?
Same reason as the last one.
Okay, so that violates the definition of injective. So it's not going to be bijective either. And what do you think about surjective? Okay, Dylan, you've got a thumbs down. Why not surjective?
Because only the positive integers are in the range, or the negative integers that are not the negative real numbers that are not a square. So they're not in the range.
Yep, sounds good. That's right. So that's right. We're not going to get any negative real numbers from this map, so we're not mapping onto the whole codomain. So we can take some value y in the codomain. Here it's a little bit confusing because the domain and the codomain are the same, but we're picking an output, a potential value in here. So that's not going to happen since we have real numbers. If we change that to the domain from R to complex numbers, okay, maybe we're getting somewhere, but that's not the case here. Okay, so clearly it's not going to be bijective since, well, both of those things are not true, but all we need is one of them to not be true. Any questions? So when you're thinking about these, what might be useful to consider? Say something like B and C and D, they're kind of pretty similar looking questions.
Like the size of the different sets.
You said the size of the domain and the codomain?
Right, yeah. I think if they're not the same size, it won't be bijective.
Yes, there is some relation between how many elements you have in the domain and the codomain in order for it to be bijective. That's right. They need to have the same number of elements for bijective, but That's not necessarily the case for those other two properties. So you can be injective and have different size sets, and you can be surjective and have different size sets. But if you're both injective and surjective, that's right, then you should have the same number of elements. How did you all, so this notion of onto, one-to-one, probably is not a new notion. I'm sure it's not a new notion to you. What sorts of things did you do to determine whether a function is one-to-one before, trying to do things more formally with proofs?
Horizontal line test.
Yeah, we can take a look at a graph, right? So this is a very visual sort of question. So the picture for these really tells the whole story. So for example, this one, right? Here's the graph of h of x is x squared. And so the vertical line test tells us whether we have a function. We draw a vertical line through. We make sure we intersect only once. Horizontal line test can be used for injectiveness. And then from the graph, we can quickly see the range, right? And make sure that we hit everything, which we very clearly don't hit everything because here's a whole bunch of values for negative values of y where we're not mapping onto that. Okay, so what do you guys think about C? What does the graph of y equals x cubed look like? You can draw it on your camera. That's right. Yeah, so it's this like chair-looking function. So is this an injective function? Okay, is it a surjective function? It is. Yay, we just have our first bijective function, right? So this satisfies both of those properties, injective and surjective. And so kind of an informal proof would be to say, well, look, every horizontal line that I draw intersects the graph. That makes it surjective, and it intersects the graph exactly once, and that makes it injective. But let's think about how we can prove this a little more formally. So that picture definitely is good, and if you've got a picture, you can kind of refer to it in a proof. But if we want to check injective, so let's say we want to prove that this function is bijective. So that would involve us showing two parts. And so just to kind of go back real quickly and take a look at what it means to be injective is we want to show that if there are two different inputs, that they should give me two different outputs. And so one way to do it is to say, well, let's assume that these two things are different, and then therefore we can show that their outputs are different. Sometimes you can prove these things by contrapositive and say, well, let's assume that f of x equals f of y. Well, then that's going to imply that x equals y, and that would be a proof by contrapositive. So let's do this one by contrapositive. So here we're going to say, let's consider two values x and y that are in the real numbers. And we don't have the f here, we have a j. And we're going to assume that j of x is equal to j of y. And then this would tell me that x cubed, which is j of x, is equal to y cubed, that's j of y, and I skipped something there, but again, if we're going to prove this by contrapositive, then what we're hoping to show is that if the outputs equal each other, then the inputs have to equal each other. And that's the contrapositive of if the inputs are not equal to each other, the outputs are different. So what's left to do to go from here to here?
Could you take
Take
the
the cube root.
Yeah, we'll take the cube root, right? So that's an algebra step there. And right, when we have a squared here, we have some issues because those aren't unique solutions, but with an odd power, that's great. So we're going to take the cube root. I'll say that, and I don't have to say that again. That might be a more formal proof. Sometimes I think it's quite often that the contrapositive is a good way to prove the injective property, because it's a little bit harder sometimes to say, well, if x and y are not equal, why is x times x not equal to y times y? Yeah, you can try and do it directly too. Any questions? Okay, surjective. So for the surjective part, again, by definition, we want to show that for all things that are in the codomain, there exists some x in the domain such that f of x is equal to y. Put that down for a sec. So that's the goal to take to prove surjectivity. So here we can say, well, we've used x and y above. So let's just pick a z that's in our codomain, which is R here. What is a real number that would map to z? So what number, when I cube it, would give me z?
1.
So I want to do this for any arbitrary number.
The
The
cube root of x.
Yeah, we could just pick the cube root of z, or whatever you wanted to call that thing. So if we pick x to be the cube root of z, then f of x is the cube root of z raised to the third power, which equals z. And that's all we need to prove for surjectivity, is that given anything in the codomain, there exists something in the domain which gets mapped to it. And so, you know, both of these things are like for all statements. If you want to prove that it's not injective or not surjective, like in the previous examples, we just needed to give a counter. One counter example is enough to disprove those statements. Okay, so I think it's good to try and do some practice on these. So maybe this is a good time to break us up and talk about some of them. Yeah, I would say we can kind of go through as far as you might go. I don't know if everybody in here has taken 3191 or 3195 linear algebra class. So if some people in your group that you're talking with have not had linear algebra, then just skip over this one and move on to the next one. Okay, so any questions about this before I break this up? So I would say, when you're working in your groups, I think it's good to like have the informal idea over here, but I would definitely encourage you to try and write up a more formal proof. If you're disproving it, then that means you just need to provide a counterexample. Okay, rooms are open. Okay, welcome back, everyone. Okay, good. So as was probably expected, yeah, so surjectivity is the new part of the puzzle here. So it seemed like that's where most of the questions were. So at least I was able to check in with the two groups about D. Were there any questions? I didn't check in with the group that Nat was working with, obviously. Any issues with that one in that group? Okay, yeah, so this one over here, then just to make sure we're clear on this, it was not injective. And to prove that, we just need one counter example. And so people came up with different ones, but these are two different outputs that both get mapped to 0, so thus it's not injective. And so the graph of it looked something like this. And so again, if you're dealing with like functions that we're used to from our pre-calculus calculus days, then I do think it's really useful to graph a picture because the picture really tells the story here. For injectivity, we want to make sure we intersect the graph at most once. For surjectivity, we want to make sure each horizontal line intersects at least once. So this does satisfy the property that given any output, there is some input that maps to it. And so if you want to do a formal proof, you could draw a picture and point out these properties on the picture. If you want to be a little bit fancier in this case, we can comment on the fact that since this function is continuous, and as we go to negative infinity, we approach minus infinity. And as x goes to positive infinity, k of x approaches positive infinity. And really, what's going on here is we could use what's called the intermediate value theorem. Okay, and what the intermediate value theorem says is that for any value in between our end limits, in this case, that there is some value of x in our domain such that f of x is equal to c. I wouldn't expect you to quote the intermediate value theorem, but it's just nice to see where that might come up. So again, a picture proof and comments about the graph would be totally sufficient here. Okay. Any questions about that? So there were some really good questions that came up with some of the groups about this. So yeah, there definitely are some subtle issues. So I'm glad that we had some time to talk about them. Okay, so in E, we're now mapping from the finite power sets of the real numbers into the real numbers by taking the product of all of the elements in the set. So what did groups think about injectivity?
It's not injective.
Okay, and what's a counterexample for that?
Maybe the set 3-2 and the set 6-1.
Yeah, quick. So there are two different sets that have the same output. So it's not injective. And what was the consensus on surjectivity? Yeah, so this is surjective. And so for a proof of this, we can say, well, let's let x be an element in our codomain. Now this is nice because the domain and the codomain are different. So we can see we're picking some real number. And again, what we want to find is some element in the domain which maps to that number. So what's a set that would give me an output of x?
It's the set of x.
Yeah, or yeah, that's right. We can pick x, we can pick 1x, whatever. Yeah, I don't need to pick the 1 in there. So that's really all we needed to see, was that there is something which maps to that number. Okay, and again, for it to be bijective, you would need a yes for both of those two previous properties. So just, we've done some examples now where you can see it's possible to be injective, not surjective. You can be surjective and not injective. You can be neither, you can be both. So these are really independent properties.
Is this kind of like with equivalence relations, where if you prove the different pieces, you automatically prove that it's an equivalence relation? Or do you have to do any more proof on bijective?
You don't need to do any more proof of bijective. So if we did like a formal proof, maybe somewhat formal back here. And so, yeah, so this proof for bijective is we just need to prove injective, we need to prove surjective, and then we're done. So there's nothing else besides those two. Okay, what do you guys think about, did groups get the F? I don't know. So here we've got the floor function, which is different from rounding in the sense that no matter what the decimal is, we just pick the closest integer that is less than it. So this injective.
No.
All right, why not, John? That's right.
Because whatever value you choose for it, it's just not going to map to itself. It has to be less than, or I don't know. It's just.
So to disprove injectivity, we need to show that there are two different inputs that get mapped to the same output. I just picked 2 just because 2 was the first thing that I saw over here. So f of 2 is 2. What's another number that would map to 2?
1.7.
1.7 would map to 1 because we're going to the integer less than it.
2.1.
Yeah, okay, so we'll pick something 2 with a decimal point over there, right? So 2 point anything is going to map to 2. So we have 2 is not equal to 2.1. So there are 2 different inputs, but they give me the same output. F is not injective. What do you guys think about surjectivity?
I think it is surjective.
All right, so let's pick something in our codomain, which is integers. And what I want to show is, oops. Is that there exists some input in R which gets mapped to this integer A. So what's something that would get mapped to A? A is an integer.
A.
Yeah, right. So, right, an integer is the floor of itself. And let me just say that the property is not in general that f of A maps to A. We just need to find something that maps to A. So it didn't have to be itself. But that's a nice choice since we know that the floor of an integer is itself. And so since it's injective but not surjective, it's not going to be bijective. So for G, I don't know if everybody has taken or will take or whatever linear algebra, but if somebody has taken it, how can we check to see whether a transformation is bijective? Does anyone know? Okay, well then we'll skip that. It's not required content, but the idea here is you could check that the determinant is not 0. And if the determinant is not 0, that means it has an inverse. And so then you can prove that any output has a certain input by taking the inverse of the function A. Okay. No fans of linear algebra here, so we will move on. So these are definitely the antithesis of the linear algebra one, in that these are totally conceptual. No math knowledge is needed here. So what do you guys think about a function that takes each person and gives them their first and last name initials?
Not injective.
Right, not injective. Yeah, and Alex is always a good counter example with myself. We would both get mapped to AS. That's right. So that is not going to be injective. Is it surjective? I don't know. Probably. We can find somebody in the world that has a first and last name that has every combination that we could exhaust.
So can we just not prove that then? So
Yeah, I mean, we can certainly prove that it's not injective.
but can we like prove that it is surjective?
You could probably get some data about from the Russians about all of our voting data. They have it all. And then you could look at those voting logs and track down all the different combinations of everybody's name. So you would have to have access to like some information. You could probably whip out a phone book if they even still made phone books, which I guess they don't, and do it that way. But yeah, in theory, you would need to just know that for every 2 pair of letters, there's some person that has those initials.
I guess what I'm asking, I guess what I'm asking is that like for these questions, like almost like, I can't remember who it was, if it was John, but like as far as handling like the equivalence functions, like proving or disproving each part, or like for this problem, like what would we do? Would we just assume that it's not, or I mean, we can't assume that it is surjective. So like how would we technically do the
Yeah, so
problem?
I'll make that out right here. So for any pair of letters, there exists a person with those initials.
So we are assuming, like what I'm saying is like we're not proving or disproving like bijectivity. We're just saying it's either not injective, surjective.
So yeah, so here's
we
a
don't
proof.
prove
Here's
that
a
it's
proof
not.
for surjective, and then the proof for not injective would be me.
Yeah.
Alex. We both have the same output. So certainly we can prove it, but since this is not a mathematical function, our proof is just going to be more of a qualitative statement.
Yeah.
Okay. So let's see, we've got a couple more minutes. Let's think about question 2 on our way out. So here we're taking a look at the function f of x is equal to mx plus b. And what we want to think about, for what values of m and b would this map be injective, surjective, or bijective? So what might be useful here?
Checking the horizontal line test to see if it passes, which it does.
Yeah, so, right, we've got this kind of general function that we're used to from most of our math classes. And so, like, it might look like that. It could be a negative slope or whatever. But here's kind of a general graph of y equals mx plus b. And so for this function, is this injective?
Yeah.
Yeah, right. And in fact, if we like set the output for any value, we could figure out what the corresponding input that gets mapped to it by subtracting b and divided by m. So this is injective. Is this surjective?
Yes.
Yeah.
It is, right? Same idea as the x cubed minus x, right? It's continuous. We're going off the positive infinity on one side and negative infinity on the other, so we have to hit everything in between. This is not true for all values of m and b. So can anybody think of a value for m that would make this
0.
So if m is 0, then we just have a graph that looks like this. In which case, right, this is really the only violation of it. So in this case, it is not injective. Everything gets mapped to the same value. and it's not surjective. So as long as M is not equal to 0, then we'll have injectivity, surjectivity, bijectivity, thus, and B doesn't make a difference at all, right? B is just a shift of this function. Okay, so I will, I think we did the tricky ones. I'll write up solutions to the ones that we didn't quite get to if you want to practice those. And then for Monday, we're going to take a look at composition and inverse functions. So I will get a brief quiz up on that material maybe towards the end of this week. So I will be getting homework and a quiz up for you guys shortly. Otherwise, have a nice weekend, everybody, and I will see you all on Monday. I've got office hours tomorrow if you have any questions.